Bismillahirrahmanirrahim. Dear students, this is a second year class and we are talking about chapter number 14. And yesterday we done the lecture number 19. Today we start lecture number 20. So we are talking about colored compounds, colored complexes. And some introduction I gave you yesterday. The transition metal compounds, they are colored. And the 3 points yesterday I told you. If you want to revise that the complex may be absorb the whole white light, they appear black. The complex may reflect to transit the whole light, they appear white. The complex may absorb some of it and may reflect or transmit the remaining light. So these are the 3 points for the colored complexes. Now the question is that why color is going to be formed? Why these transition metal complexes impart colors? The explanation is given. This is very important. This is the chemistry of color of the complexes. How? So the explanation is that when the transition elements make compounds, when the transition metals make compounds, then the color of the d orbitals are involved in the bonding. You know, these are called d block elements. These elements are called d block elements, means d electrons involved in the bond formation. Then the electrons of d orbitals are involved in bonding. This is the one point when colors are going to be formed. For this reason, the d orbitals are split into 2 levels. D orbitals which are participating in the bond formation, they split into 2 levels. One group of d orbital gets little higher energy than the group of other orbital. Means one has a lower energy d orbital group and other has a high energy d orbital group. One has a little bit higher energy of one group and second group has a small energy for the d orbital. So 2 groups we have. Now the electrons which are present in the lower d orbitals, the electron which is present in the lower d orbitals absorb the photons of energy and promoted to higher energy levels. You done in the previous classes when electrons jump from lower ground state to higher excited state, the amount of energy will be absorbed. So that's the amount of energy is going to be absorbed when the electron present in lower d orbital absorb the photons of energy and promoted to higher level. What happens? The photon which is involved for jumping electron is responsible for showing the definite color. The photon which involving for the jumping electron is responsible of the showing definite color. Basically, unabsorbed light, the light which is not absorbed, is transmitted. Basically, unabsorbed light is transmitted and it decides the nature of the color because of 2D levels involved, but one is a little bit higher level and other is a lower level. Both are D, so that's why we call D transitions. Maybe short question asked, what is the D transition? This is the explanation of D transition and how the transition compounds complexes impart their colors and how the electron is transferred from the lower level to higher energy level, and some of photons are going to be absorb the light. So students, these are the transition metal atoms and ions. They impart their colors. Zinc positive 2 and titanium positive 2, they are colorless. And titanium positive 3 purple, copper positive 2 blue color, vanadium positive 3 green, nickel positive 2 green color, chromium positive 3 deep green color, cobalt positive 2 pink color, chromium positive 2 blue color, iron positive 2, that's a very light green color, and iron positive 3 will give a yellow color. So these are the number of ions, and they have number of unpaired electrons. So you notice that zinc positive 2 and titanium positive 4, they have no unpaired electrons, they are the low color. So then you can see there are the unpaired color stars 1, 2, 3, 4, 5. Iron positive 3 have 5 unpaired electrons and give yellow color. So these are the transition metal ions. They impart in color depending upon the number of unpaired electrons in the d orbital. So students, this is the coloration of transition metal ions or compounds complexes. So these are the quick quizzes. Why do the most of transition metal ions possess definite color? This explanation. This explanation you have to write. When complex compound appear black, in first point, color complexes, the answer is given here. What is geometry of complex compounds having coordination over 2 forces? Already we discussed this. Give examples of hexadentate and tridentate. Already we discussed these points. You should go through the topics. You will find these answers. You have to complete these ones. Now new topic will start. We are going to start new topic. Some important transition elements. Some important transition elements. We will discuss about some important transition elements. So number one, we start number one, which is called vanadium. Vanadium. Symbol is V capital. Chemistry of some important transition element. Number one is a vanadium. This is the topic we discussed. Now 2 points are given here for the vanadium element. Number one, the conversion between various vanadium oxidation states. This is a number one topic. The conversion between various vanadium oxidation states. This is number one. And number Number 2 is the use of vanadium oxide. The use of vanadium oxide. Vanadium oxide V2O5 we call vanadium pentoxide. This vanadium pentoxide is used for the preparation of sulfuric acid in contact process, where 100% pure sulfuric acid is prepared. First, sulfur changes into sulfur dioxide gas, then sulfur dioxide gas changes into sulfur trioxide gas in the presence of vanadium pentoxide, which is used as a catalyst. The catalyst substance may be element, may be compound, maybe two elements combined, maybe two compounds combined, which accelerate the chemical reaction, which speed up the chemical reaction is called catalyst. So, dear students, the point number 1, vanadium conversion between the various vanadium oxidation states. If you see your book, the vanadium shows many oxidation states, even -1, -1, 0, +1, +2, +3, +4, and +5. So vanadium shows in different compounds, different oxidation states, and you done the properties of the transition metals. These oxidation states or oxidation numbers depend upon the number of unpaired electron. More the number of electrons unpaired, more will be the oxidation states. So compounds in lower oxidation states are very unstable. These are lower. Mostly 4 and 5. They are stable. Lower oxidation states are mostly unstable, and which is written here, most stable. Most stable oxidation state of vanadium are +4 and +5. The reason for variable oxidation state, I told you that d electrons in addition of s electron for the purpose of bond formation and also unpaired electrons. You done the previous properties of the transition metals. Initially we done this. Transition metals, they involve d electrons with s electron for the purpose of bond formation. So energy of n-1 ns orbital is very close to each other. So the n-1 d electrons are easily lost as ns electrons. So in the higher oxidation state, s and d electrons are used for bonding. So when the s and d electrons are going to be used, so they give different types of oxidation states. Now examples, we have many examples. I'm going to write some examples here. Few examples I'm writing here. Suppose vanadium shows -1 oxidation state. -1. So simple example I am writing here. Like this one. So complexes, this is the carbonyl group, which is a neutral, and this is the vanadium, and here on the complex -1. So this -1 shows the oxidation number of vanadium, because carbonyl group is a neutral. And you can see from here, suppose I am going to write for the vanadium plus 3 compounds. So V2O3. Oxygen is -2 multiplied by 3, -6, +3 multiplied by 2, +6. And you find other also examples for oxidation number 3. If you see for the oxidation number 5 for the vanadium, so this one is vanadium pentoxide. Oxygen is -2 multiplied by 5, -10, plus 5 multiplied by 2 plus 10. So vanadium has a 5 oxidation state, and then the halogen is going to be present. So this shows +5 oxidation states. So you can see many. +1, +2, +3, +4, +5, -1, 0 maybe. So these are the oxidation states of the vanadium and from different compounds. Now we are going to discuss students, we are going to discuss another topic that's called conversion. How we observe. Observing the changes in the lab, in the laboratory. So A is reducing vanadium 5 oxidation state. Vanadium 5 oxidation states to vanadium 2 oxidation state. Decrease in oxidation number is called reduction. So in the laboratory, when we are going to do the experiment, how vanadium reduces, change vanadium 5 oxidation state to vanadium 2 oxidation state. How this change takes place in the laboratory. See here, physical state and dissociation of vanadium pentoxide V2O5. And you know, in the vanadium pentoxide, oxygen is -2 and vanadium is +5. It is a yellowish red poisonous. It is a yellowish red poisonous powder having melting point 670 degrees Celsius. 600 melting point 670 degrees Celsius. Poisonous powder, yellowish red poisonous powder having 670 melting point degrees Celsius, slightly soluble in water, and resulting pale yellow solution is acidic. If you dissolve in water, so it is partially soluble in water, yellowish color appear, and if you test this solution by using the pH paper or other litmus paper, if not color, or you have to use a pH meter, so it shows acidic, slightly acidic in nature. So it undergoes change from positive 5 to positive 2. So this is the vanadium pentoxide. I told you -2 and +5. This is oxidation number of vanadium +5, and it is going to be converted into vanadium tetraoxide plus oxygen gas is going to be evolved. So oxygen is a -2 multiplied by 4, -8. So this should be a +4. Now in the first step you are seeing the vanadium +5 reduces to +4, but we want +2. In the step number 1, this vanadium 5 reduces to vanadium 4. Then, if you see the next page, 74, page number 74, conversion of ammonium NH4 3 to vanadium pentaoxide, vanadium 5 oxide, ammonium metavandate. The name of this is ammonium metavandate. Ammonium metavandate changes into vanadium pentoxide 5 oxidation state. Students, this vanadium pentoxide +5 oxidation number, if I use aluminum as a reducing agent, so this vanadium converts into aluminum trioxide, means aluminum is going to be oxidized, and vanadium 0. Vanadium 0 oxidation number. So this reduction +5 to 0 means reduction of 5 electrons in one vanadium. So this is the reduction. The exact vanadium ion present in a solution is very complicated and varies the pH, change the pH of the solution. The reaction is done under acidic conditions when the main ion present is So here oxygen 1. So this is called, this complex is called di, because oxygen is negative, so we call dioxovanadium 5 ion. Dioxovanadium 5 ion. Oxygen 2 dioxo ligand. Vanadium is here and oxidation number of vanadium is 5. Charge is there, I put ion. So dioxovanadium 5 ion is going to be formed. Now here practically in the laboratory, how this vanadium reduces from 5 to 4. Positive 5 to positive 4 practically. If you see the page number 74, the reduction takes place in the presence of HCl and zinc. In such reactions, hydrogen gas is produced, due to which the reduction takes place. In the formation of hydrogen, then reduction takes place. Due to the change in oxidation number of vanadium positive 5 to positive 4, the color also change takes place. The green color is transition state, intermediate state in between yellow and light blue color. You are seeing the light green color, which is an intermediate in between. Mixture 5 yellow and 4 blue. This is a mixture. So you are seeing in the first titanium floss. So this is a closed with a cotton. It should not be oxidized. It should not be contact with the oxygen. And oxidation state of vanadium is 5, and which is called dioxovanadium, which already I told you written there. So this is like this color. This color is yellow color. Then after changing, you will get a transition state. This transition state, you will get a new oxidation state of the vanadium, which is mixture, which is intermediate. The green is a mixture of original yellow and blue. This is a mixture of original yellow and blue, and it is going to be changed into the oxidation number 4. The formula is like this one. Like this one. So this color is a yellow color, and this color is a light blue color, and mixture shows a green color between oxidation level 5 and 4. So oxygen negative 2 and the vanadium positive 4, negative 2, you will get positive 2 here. So dear students, this is the conversion of oxidation number 5 to 4. So we are going to finish here, because we start this lecture continue tomorrow also, and there are many other transition matters. They are very important, and we will discuss tomorrow inshallah.